So here we are doing some polar graphs, which you guys have already done a few for your little activity. So you should recognize yours because I think we are going to show one of each kind. And it's going to be our last new section before spring break. And we're going to take a quiz on it, this and the polar coordinates, on Thursday. So, polar equations use r radius and theta angles instead of x and y. So not just only the points r and theta, but also the equations. And we'll start with the most basic two equations. So just like x equals a number, or if y equals a number, those are straight lines like horizontal lines and vertical lines. The same thing, you get the most basic shapes from the radius. You get a circle. And from theta, you get a line. And the definition of a polar graph is the set of all points that make the equation true. Just like a line is the set of all points that make up the line. Every point on the line makes a true statement. So here's a couple of examples of these pretty simple graphs. The first one is when r equals 2, so the radius of a circle that equals 2. Radius equals 2, there it is, 1, 2. Then we have when theta equals pi over 6, it's just that pi over 6 line. The positive is going towards the pi over 6, and the negative is going away from it. And then you have another radius of 3, so it's that circle. 3 radius all the way around, that's a terrible circle. And the last one is 2 pi over 3 makes a line. And you'll be able to use your graphing calculators for these, so you'll see what they look like. The thetas you'll probably have to remember because those won't go in your graphing calculator. So just like regular graphs, rectangular graphs with x's and y's make a shape, parabolas, they can make circles, they can make all kinds of shapes, not just lines. Polar graphs make some crazy shapes a little differently, but you still have points that you connect the dots and make the shape. So that's what we're going to do. We are going to start graphing the points like we did from the polar coordinate lesson, the last lesson. So I'm going to start at 0, 1, and then pi over 6 is at 0.9. So pi over 6 is just before 1. Then pi over 3 is at a half. So pi over 3 is at about a half. And pi over 2, which is 90, is at 0. Then we have 2 pi over 3. Now 2 pi over 3 is going negative a half, so it's going away from 2 pi over 3, so it's going to be down here at a half. And my 5 pi over 6 is also going away from 5 pi over 6 at 0.9, so that's about right there. Now you're going to see, let's see what happens for the rest of these graphs. So if I do pi, which is 180, also going negative away from the 180, I'm going to end up at the same spot that I had 0 at. So this, and then 2 pi is the same thing. Those are all the same point. So let's see what happens at the next one. So 7 pi over 6 is over here, and I am going away from it to 0.9. It's the same as pi over 6. So those two are the same. And I think this is going to happen a bunch if I do the pi over 3. it's the same as 4 pi over 3 in the negative direction. So pi over 3 and 4 pi over 3, those match. Pi over 2 and 3 pi over 2, also both match. 2 pi over 3 matches with the 5 pi over 3 going in the opposite direction. The 2 pi over 3 was negative direction, 5 pi over 3 is positive direction, same point. So those two match. And of course 5 pi over 6 was going in the negative direction, so 11 pi over 6 is going in the positive direction, and they are meeting at the same place. So we have a bunch of matches. Now I'm going to connect the dots. And I started at 1, and I'm going to go around like the points did. And I made a circle. So you don't necessarily have to do from 0 to 2 pi every time. A lot of the time it's going to just be right here to pi. So, and I wanted you to notice that we are plugging in thetas to get r. So instead of plugging in, so even though the r comes first as a point, it's theta that you plug in to get r. So that's what you want to get there. Now, a lot of these graphs have symmetry. And so once you figure out where the symmetry is, you can plot the other points. So let's go ahead and do this. We're going to do some points, and we're going to see if it has symmetry. So I'm going to do 0, negative 1. So that means from the 0, I'm going to go in the opposite direction. Okay. Then I'm going to do pi over 6, again, in the opposite direction from pi over 6 at 0.7. So that means about right there. Then pi over 4 this time at negative 0.4. So negative 0.4 on that pi over 4. It's about right there. Then pi over 3 is at 0. And I'm going to keep going with pi over 2 at 1, so 90 is 1. Then we have 2 pi over 3 at 2, so 2 pi over 3 at 2, so this is a little different graph. And then 3 pi over 4 at 2.4, so 3 pi over 4 at 2.4 is about right there. And 5 pi over 6 at 2.7, it's about, doesn't like my dots. I'm going to make them messy. Okay. And then pi is at 3. Pi is 180, is at 3. Now notice we have a lot of points that are kind of, if I draw this like that. So this kind of looks like a spiral, but we need some more information. So I'm going to go ahead and plug in I'm going to see if this is symmetric. So I am going to go, everything is on one side so far, and I am going to plug in the symmetry and see if this is a symmetric graph. And so I'm going to use purple this time. So if it's symmetric over pi, or 0 line, or you can even say x-axis, and I'll be happy because I know that you understand where that is. So if it has symmetry over that, the 7 pi over 6 is going to match with symmetrically with the 5 pi over 6, and so that was right here. And if the 5 pi over 4 line matches with the 3 pi over 4 line, that's about right here. And if 90 matches with 270, that's at 1. Okay, and if 2 pi over 3 matches with 4 pi over 3, that was at 2. If 3 pi over 4 matches again, we got that right there. And then this point is going to match about right there. And I'm going to continue my curve now. So I'm going to go all the way around here and match it up there. And I don't know if you can see that, but this is an inner loop lemicon. So this one had symmetry like this, and I'm going to show you that the spirals, if you did a spiral, you will know that the spirals start at 0 and they go out instead of curving back in. This one kind of slowed down, and the spiral will continue on out. That's how I knew that this was not a spiral. So let's go to the next one. So on this one, we are given the equation this time, and we are going to plug in these points and see what the shape makes now. So these are all in radians. So using radians, be in radian mode. So if you're going to plug them in as radians, since that's in the table, then you should use radian mode, and that will give you the right answer. But if you want to use degrees, you can convert these all to degrees and do it that way. So for 0, I'm just going to go ahead and fill these in for you to show you what I got. I started with 2. When I plugged in pi over 6, I got 2.5. For pi over 4, I got 2.7. For pi over 3, I got 2.9. And for pi over 2, I got 3. Then at 2 pi over 3, I got 2.9 again. 3 pi over 4, I got 2.7. 5 pi over 6, I got 2.5. And you guessed it, at pi, I got 2. So this has symmetry, and there you can see what it's around. The symmetry is around pi over 2, or the y-axis, if you would rather. Either line is fine, however you want to call it. So let's go ahead and plot these points. So 0, 2, that's easy. Then pi over 6, 2.5. Pi over 6, 2.5. Then pi over 4, 2.7. Then pi over 3, 2.9, almost a 3. Then at pi over 2, it is 3. Then we go back down. 2 pi over 3 is 2.9. 3 pi over 4 is 2.7. 5 pi over 6, 2.5. And pi was 2. Now, I can see the symmetry here, but I think I might need a couple more points to actually determine where. So it is symmetrical like this, but I need to know what happens below that line. So I do need a couple of more points. So I am going to go and do these right here, this, this, and this, and see what happens. So for 7 pi over 6, I'm going to get 1.5. For 5 pi over 4, I got 1.1. And you just use one decimal place when you plug these in. And then for, I went ahead and did 3 pi over 2. I went ahead and did 3 pi over 2. I did this one, I didn't do that one. And that was 1. So at 7 pi over 6, it was 1.5, 1.5. For 5 pi over 4, it was 1.1, so it's getting close to 1, very close to 1. And then for 270, the 3 pi over 2, it was 1. And I already know that it has symmetry, so I can go ahead and plot 1.5 on the 11 pi over 6, because 7 pi over 6 and 11 pi over 6 are symmetrical around over the pi over 2 line. So I'm going to plot that point. And also the 5 pi over 4 is symmetrical to 7 pi over 4. So if I folded it, it would come to 1.1. And then there's our graph. Okay. And this one is called another lemicon. I think it's the convex. Yes. This is a convex lemicon because it kind of comes out. It's not quite a circle, and I hope you can tell it's not really a symmetrical circle. It is a little different. So, and I'll go over that in a minute. So here comes another one, another shape. So this one's a little different. We're going to plug these in and I will tell you what I got. And then we're going to determine if it has symmetry or not. So I have 2, 0, pi over 6 was 0, pi over 4 was negative 1.4. Pi over 3, pi over 2 is 0, 2 pi over 3 is 2, 3 pi over 4 is 1.4. I'm feeling some symmetry here. I don't know for sure though. Then 5 pi over 6 was 0, and pi was negative 2. Okay, so I see some similar things. Let's go ahead and plot these and see what actually happens. So 0 is 2. Let me go back to green. That's a little brighter. 0, 2. Pi over 6, 0. Pi over 6, 0. And we're going to have to remember this order here because we're going to make these, draw this shape. Pi over 4, negative 1.4. So that means on the other side, about right here. Then pi over 3, negative 2. So about right here. Then pi over 2 was 0 again. Then 2 pi over 3 was 2. These are going all over the place. 2 pi over 3 is 2, so I don't see any symmetry so far. 3 pi over 4 3 pi over 4 is 1.4, so about right there. 6 is 0 again, and then pi is negative 2. Oh, back to 0. So I didn't have to do any more. Now some of these graphs you can do more points, but I'm looking at this, and if I looked at the sheet, if I looked at the page, page 546 with all the graphs on it, I would be able to see that this is this graph right here. Just by those points, I can tell it kept going back to 0, so I can tell that it's going to make this shape. You are also going to have your graphing calculators to see the shape, so as long as you give me some points and fill in some points, plugging in the thetas, and then you can have some points and you can connect the dots because you're going to have your graphs. It's not going to be like a I have to get more points kind of thing. You plot some points that you in a table, you look at your graphing calculator, and then you look at the chart and say, okay, this is a rose. And you don't even have to tell me what kind of rose it is. This is a rose. Okay, I only have a couple more. So, because I want to do one of each type. So this one is different. And if you did a lemniscate, know that it's the only one with the r squared. So what we are going to do for these last two is, if you have an r squared, it is a lemniscate, but we still have to sketch it. So that means we're going to put it in our graphing calculators, but if it's got the squared on it, you'll have to take the square root. So we're going to take the square root of both sides and leave it square rooted. Do not change it into a 4. It will mess up your drawing. It's got to be like this. It's got to be square root of 16 sine 2 theta. And when you plug this in, you are going to get a couple of points. Hopefully you will see the couple of points. You can estimate where they are. Like if I go out to 3, to R3, it goes up, it actually is 30 degrees is about 3.5. So you can plug in some of these points to see where they actually touch. So about 3.5 for 30, or pi over 6, depending on what mode you're in. And then 60 does the same thing. It also matches up. 0 is on there. And then it has symmetry. So it's also got this point and this point. The 210 and the 240. And if you know what this looks like, a lemniscate looks like, it's kind of a propeller with just 2 propellers. Like that. And I'm obviously just going to say if you've got it close, then you're fine. And all you had to do is plug in a couple of points so you know approximately where it is. You could have plugged in pi over 4. Could have plugged in, well, I think all those other ones are, yeah, the other ones are 0. So you would have had to do pi over 6, pi over 4, pi over 3 to get those. And this last one is r equals 3 theta. To get the name, if you just look at the equation, I am perfectly fine with that. Tell me the name. For this one, when there's no sine or cosine, it is a spiral. And you can just say spiral. You don't even have to say of Archimedes. I'm fine with that. Just a spiral is fine. And it will be obvious on your calculator. But when you get this, so it does start at 0. And the 3 tells you how fast it's getting bigger. So I think my first one was at like my pi over 6 was just before 1. My pi over 3 is like 2.5, or yeah, 1.5. And then my 90, oh, my 90 was actually at 5. So I had to do like a 2, 4, 6 on this graph. So it was 2.5. That's what I thought. It was like 3. So it's like 1 for the first one, 3 for the second one, 5 for the next one, approximately. And then after that, they got big fast. So that's what happens with these spirals. So like my 3 pi over 4, I think that was like 8 or something. So it just starts getting big really fast. And so that's why I even had to adjust my scale on my graph here. But you are going to have your graphing calculators. You're going to have that page 546. So as long as you can just plug things in, you can graph your graphs and name them. And thank you very much. Make sure you ask me questions.